Hi, hello again. When studying linear dynamics, most of the times we're not going to have analytical expressions to play with. So, in order to extract information about the dynamics of the system, we're going to need other tools. One old friend is the phase space, a space that represents the system with one single point that defines its position and velocity. Of course, this space can be two-dimensional if the motion is one-dimensional, but it can be six-dimensional for a three-dimensional motion, or 12-dimensional space for two particles moving in 3D space. In order to get the velocity of the particle, it can be interesting to extract it from the energy of the system. If the total energy is the kinetic plus the potential, then the velocity is the square root of E minus u of x. Let's start by assuming that we have a curve for u of x. If we draw a horizontal line representing the total energy of a particular system, we know that the distance from this horizontal line to the potential energy, it is equal to the kinetic energy. So this gap is proportional to the velocity square. And from this we can draw the lines of the trajectory of the system in phase space. Let me draw different horizontal lines corresponding to different total energies of the system. From them I can draw the trajectories in phase space for different energies of the system. Under this potential, the particle will go from the right, where it has no velocity, to the left, where it has no velocity, passing by the center, where it has maximum velocity. The motion under this potential will be back and forth, so the velocity will be positive, but also negative. At the rightmost position, the particle has zero velocity, then moves to the left with negative velocity, reaches zero with maximum negative velocity, then reaches the leftmost side with zero velocity, and then moves right with positive velocity, and so on. For a symmetric potential, we would get an ellipse or a circle, but for a non-symmetric potential, we get asymmetric trajectory in phase space. Because the energy of the particle is below the local maxima, the particle is trapped in this potential. Its motion is limited to be inside here. If the particle had an energy equal to the energy of this minimum, the particle will not move. This minimum is an equilibrium point. If you let the particle in that point, it will remain there. This equilibrium point is an attractor. This attractor is a stable attractor. Just perturb the system a bit and it will still be attracted to it. It will want to move towards it. We can have unstable attractors, points such that if you put the particle there with that precision and that velocity, the particle will remain there. But if you perturb the system with a tiny bit, it will fly away from the attractor. That's why we call it unstable attractor. Let's draw the phase space trajectories around an unstable attractor. If the particle is at the right side approaching the potential, it moves with negative velocity. It will reach the potential, it will increase its velocity until reaching zero velocity, and then will bounce back, moving away with positive velocity. Same for the left part of the potential. What if the particle has enough energy to continue moving from the left to the right or from the right to the left? Well, then, as the particle approaches the potential from the right, it will increase its velocity but will not become zero. It will reach the origin with still some non-zero velocity. As it moves away from the potential, it will gain velocity. Same happens if it comes from the left to the right. There is another kind of attractor in nonlinear systems. Let's go back to the damped harmonic oscillator, and let's consider a damping term that can be positive or negative. If we write this differential equation, we have that damping will be positive if a squared is smaller than x squared, and negative otherwise. This is called the van der Pol equation. I am going to plot the trajectory of this system in phase space numerically. I will use just Excel for that. I'll take a to be 1, mu to be 0, 0.1, omega to be 1. The initial velocity will be set to 0, and I will explore what happens for different initial values of the position. Let me create the position, the velocity, the acceleration, and the time increment delta t. So delta t, I will set that to 0.02, then the initial position, let's say it's 2.2, initial velocity is 0, and the acceleration, I will use that equation. Mu was 0.1, so it's going to be minus 0.1 parentheses x squared minus 1 multiplied by the velocity minus the position x. Now I'm going to drag the time interval, and then what I'm going to do is I'm going to approximate as we've done before. The position is going to be the initial position plus velocity time, and the velocity is going to be initial velocity plus the acceleration multiplied by time. And then I'm going to drag that and then I'm going to plot the first column as the x-axis, the second column as the y-axis, because that will be the phase space, which will be velocity versus position. So now let's put the initial conditions in 2, and we see that the trajectory is not close anymore, but it goes from those 2 to a value of 2.2, and if the initial position is 1.8, it also seems to tend to that limit of 2.2, and for 2.5 also happens. So if independently of where we start the initial position, it seems that the system tends to a limit trajectory, to a closed loop that has a maximum position of plus 2.2 and minus 2.2 as the minimum. It doesn't matter if we start for smaller values, it increases until it reaches that 2.2, and if we start at higher values, higher than 2.2, then the trajectory shrinks, looking for that limit of 2.2. This is a limit cycle. The system tends to it no matter where it starts. It is not a fixed point in phase space, but a whole trajectory. The system tends asymptotically to that cycle. It is an attractor, but the position is not just one and the velocity is not just one. It is a limit behavior, a limit dynamical behavior. So we have fixed points that can be stable attractors, unstable attractors, and then we have limit cycles as time evolves to the future. All these in non-linear dynamical systems. May the science be with you.